Welcome to the topic on finite element solution for a 1D steady state heat transfer analysis. My name is Muttanna Bandar, SG Balekandre Institute of Technology, Belgavi. Today we will try to understand what is the heat transfer and what is the importance of the heat transfer in a mechanical equipment during their operations. So this topic deals with the study of a heat transfer involved in the operation of equipments. Let us consider an uh, manifold, exhaust manifold. Example of an exhaust manifold, like this portion is a web. So these are the ports of the exhaust manifold wherein they are connected to the engine head side. So let me consider this. It is a 3-cylinder engine head, and each of these are connected to each cylinder exhaust ports, and the hot gases flow into this web and they are collected at the other end and it is thrown out to the atmosphere. So this is a atmosphere. During this process, the hot gases flow through these vents. During the process of transformation, some of the heat is absorbed by the solid metal of this exhaust manifold. And also we know that when the heat is absorbed by the metal, the metal will try to expand because of the thermal expansion. And when the metal try to expand because of the boundary conditions, like this portion is fixed to the head, this portion is fixed to the head, this portion is fixed to the head, and this on other hand is connected to the exhaust valve. So there are some boundary conditions here, 1, 2, 3 and 4. At that point, because of the temperature, this wave will try to expand in this direction and this will try to expand in this direction. Might be in any direction. Let us assume that it is expanding in this direction and this in this direction. Because of this, a tensile kind of force is created at this joint. So when this tensile force is acting at this junction, it will try to pull each other and a tensile stress is produced, is induced. Tensile stress is induced. So it becomes very important to understand the heat transfer in any design system, because they will greatly influence the performance of the structure as well as what are the uh, also it will help us to understand to design the components as per the factor of the safety. So for that, this study of a heat transfer is a very important task. The addition or a removal of a heat from the system will greatly influence the performance of the system based on the boundary conditions. Similarly, like the body gets stressed if the heated body is not allowed to expand freely. So that we have seen in the exhaust manifold. Like if we try to restrict the boundary conditions, if we try to restrict the expansion, the stresses will be developed at the junctions. Like I showed, at these junctions, there will be stresses that will be developed. So in the sense, the stresses developed due to the resistance offered by the body against the thermal expansion is termed as a thermal stresses. the thermal stresses are directly proportional to the temperature gradient, so it is important to determine the temperature distribution within the body. So with this, to study the heat transfer analysis, we have to understand some of the equations. So one basic equation is a energy balance equation as per the law of a conservation of energy, which is given as E in plus Ez is equal to E out plus IE. Here there is a dot term. So in this sense, it is basically the rate of energy per unit time. So it is the rate of energy with respect to a time. So the dot indicates the rate of energy, and this E in is the heat energy input to the system, and E generated is basically when we add a heat to the system, there will be some reactions that will be happening within the system, and because of that, energy is generated within the system. So Eg is the energy generated within the system is equal to energy out. E out refers to the energy out that goes out of the system, and this E internal energy refers to the internal energy of the system. So that is the net work done by the system. Hence, the energy balance will help us to understand the rate of energy that are distributed in a different forms. So another equation in the heat transfer analysis is a rate equations, we call it as. They are also called as the laws of a heat transfer. So laws of a heat transfer quantifies the amount of energy being transferred per unit area. So already we know that what are the laws of a heat transfer, like one is conduction, convection and radiation. Now let us consider, just have a look at this image. So here uh, in the picture you can see a hand which acts as a natural sensor just to feel the sense the temperature. Like, let us consider a conduction. Like in a conduction, what happens, a person is holding a solid rod at one end, and the other end of the rod is exposed to the fire, and over a period of time the heat is transferred from this position to this position. So over a period of time we can sense the a change in the temperature here. Now how it has transferred? So basically it has transferred through the conduction, wherein we can define conduction as the rate of heat transfer through the body without the actual motion of the mass is termed as conduction. So in the sense, the heat flows from one point to another point without the actual transfer of the mass, or the actual motion of the mass is called as a conduction. Similarly, in a convection, we can find there is a heat source body, and the other body, which is a sensor, I am saying here, hand is a sensor, is at a certain distance away from the heat source, but still over a period of time we can feel the heat on our hand. So that is being transferred through the air medium. So in the sense, we can define convection as a heat transfer between the body and the surrounding medium. Here surrounding medium can be air or any fluid, and that fluid will have some property what we call it as H, which is a heat transfer coefficient of a medium. It has some heat carrying capacity, so that is termed as a H. Now the radiation is nothing but the process of a heat transfer or a heat exchange between the two body. So this is one body and this is another body, and the heat is being transferred from this body to this body in the absence of medium. So here there was a medium, but in radiation, even in a vacuum, the heat can be transferred from the one body to another body. So that we call it as term it as radiation. So basically it is a exchange of a heat between the bodies in the absence of a medium. So once we understand the definitions of conduction, convection and radiation, now we can put them into a mathematical form as, so this is the definition of a conduction. Conduction is a transfer of a heat through the material without a net motion of the mass of the material. So that is given by a rate of a heat flow. Also it is called as a Fourier's law, which is given by capital Qx is equal to minus k into a dt by dx, and where Qx is a rate of a heat flow, k is the thermal conductivity of a material, which is a property of any material, and A is the cross section area. If I take a rod, circular rod, so this is a cross section area, and dt by dx is nothing but, if I take this as a t1, this as a t2, so dt is t2 minus t1, dx is nothing but a x1 minus x2. So that dt by dx can be referred as a temperature gradient. So they are given as this way, and dt by dx is the temperature gradient expressed in kelvins per meter. Similarly, we can define a convection as it is a heat transfer process by which thermal energy is transferred between the solid and a fluid surrounding it, and mathematically it can be expressed as, the rate equation is given by Newton's law of cooling as Q is equal to H A into T minus T infinity, where Q is a rate of a heat flow, H is a convective heat transfer coefficient, which is a property of the medium, and A is the cross section area of the exposed surface. If I take this as a hot body, this is the exposed surface and these are the air surrounding it, and T is a surface temperature and T infinity is the temperature of the surrounding media. It can be air or any fluid. So it can be given in this way. Q is a convective heat transfer rate, H is a convective heat transfer coefficient, T is the temperature of the surface of the body, and T infinity is the temperature of the surrounding medium in a Kelvin. Similarly, the radiations can be defined as, it is a heat transfer process by which the thermal energy is exchanged between the two surfaces in the absence of the medium, and mathematically it can be expressed as, the rate equation is given by Q is equal to sigma into epsilon into A into the difference of the fourth root of a 4 power of a temperatures. So this is a temperature of one body and this is the temperature of another body. So where sigma is nothing but a Stefan Boltzmann constant, and epsilon is nothing but emissivity of the surface, and A is the surface area of the body through which the heat flows. After understanding the basic equation and the laws of heat transfer, let us derive the differential equation for a 1D heat conduction. So 1D refers to one dimensional. Like I have a three dimensions actually in a reality: X, Y and Z. Now when I say a one dimensional, I will be studying what is the heat that is transferred in a X direction or in a Y direction or in a Z direction. So for a convenience, let us consider the heat transfer in a X direction. Consider a cube body. So this is shown in a 2D, like 3D will be something like this. So this is a wall and this is a cross-sectional area. So I can say this is a area and this is left face and this is a right face. So here I am indicating, and this is the length along which I want to study the heat transfer. So let Qx be the heat flux entering the wall. So Qx is the heat flux that is entering, means I am heating this surface. And let Qx plus dQx by dx into dx be the heat that is leaving the right face of the cube, or that is the heat flux leaving the wall, other side of the wall. And capital Q A into dx be the rate of a heat generated per unit volume. So Q is the amount of a heat that is generated within the body, because when I heat it, because of some reactions, the energy is generated here. So that is termed as capital Q, and A into dx is volume. Like if I take this as a cross section area, so how much of the energy is developed, this area into dx will give the volume. How much of the heat is generated in this volume, be the Q into A into dx. So from the equilibrium of the body, we can write heat rate entering the volume, that is Qx, plus heat generated within the wall, that is A into Q into dx, is equal to the heat leaving the volume. So this equation is referred earlier in our basic equation. So the energy balance equation. So once using that relation, I can rewrite the equation as heat rate entering, heat rate generated, heat rate is equal to heat rate leaving. So I can write Qx into A plus Qa into dx is equal to Qx plus dqx by dx into area. Let us name it as equation 1. And from a Fourier law of a conduction, already we have done this. Qx is equal to minus Kx into dt by dx, amount of a heat flow. I will substitute this Qx into this. So wherever Qx is there, replace that with this equation. So I will substitute here, here and here. So it is shown in next slide as, so this was a Qx term, A as it is, Q into A into dx as it is, this is Qx again, and there was a Qx term here. Now from this equation I can cancel these two terms because they are same and equal and they are on either side of the equation. And this A and this A gets cancelled, this dx and this dx gets cancelled. The remaining quantity will be q in is equal to minus d by dx into k into dt by dx. And if I take this term on a left hand side, it will be d by dx k into dt by dx plus q is equal to 0. And this equation 2 is called as a governing differential equation for a 1D heat transfer. And q can take a positive value when the heat is generated within the system, and q can be negative when it consumes the heat energy, like it can be a sink. So these differential equations is similar to what we have derived for structural moment, like it was dx square by d square u by dx square. So where u was the displacement plus m is nothing but a moment. So we can compare this equation to the structural. But here the field variable was displacement in structural, and in thermal field variable is a temperature. I was studying what is the nodal displacement in structure, but in thermal I will be studying what is the nodal temperature of the system. So that's the only difference between the structural and the thermal in case of a conduction. So now let us derive the conductivity matrix. We call it as a conductivity matrix. In a structure we call it as a stiffness matrix, and in a thermal we call it as a conductivity matrix. I will consider a element whose length is Le, that is x2 minus x1. So this is x2, this is x1, the distance from the global axis, and x2 minus x1 will give the length of this one. And let the temperature of at a node 1 be a T1, and temperature at a node 2 is a T2. Now if I consider this one from the stiffness matrix, we know that K is equal to integration of B transpose D into B matrix into dV. So this is with respect to volume. Now how we have got this equation was, already we have done this in a structural part. Let me explain once again. Like if I take this as a stress strain curve, and since we are interested only in elastic term, we are working only within the elastic limit, then this is area of a triangle. This was sigma stress, this was strain. If I take the energy stored in the system, U can be given as 1 by 2 into sigma into epsilon, area of a triangle. Now I can substitute this sigma as 1 by 2 from Hooke's law as epsilon into E into epsilon. So this epsilons are nothing but this B and this B. We call it as strain displacement matrix, and this E is a Young's modulus, which is a constant in a structural, and this D will act as a thermal conductivity in our thermal analysis. So hope you are clear with this, how we have arrived for this equation. So using this equation, now I will try to find what are the safe functions. So safe functions are n1 and n2. I told like the safe functions will take a maximum value at that corresponding node. Like if I take this as n1, the value of a safe function is maximum at node 1, and gradually it will decrease and become 0 here. Similarly, the safe function at a node 2 will be maximum here and it will gradually drop here. So using this, I have written here n1 and n2 and differentiate this n1 and n2 with respect to x. So that will give the a strain matrix. So dn1 by dx, dn2 by dx. So if I differentiate this, it will be a minus 1 by LE, because if I differentiate this one with respect to this one, so this is a constant, goes off, minus x is 1, differentiation of x is 1, so minus 1 divided by LE as it is. Similarly, if I differentiate this one, so it carries a positive value, differentiation of x is 1 and divided by LE will give the this term. So once I get this, I can take a transpose of this B, so wherein rows are converted into column. So this will become a column like this. So I will write B and B transpose as shown here. I will be using these two matrices, substitute them into this and this, and try to integrate and get the what is called as a conductivity matrix. So let us do that. So Kc stands for a conductivity matrix, is equal to integration of 0 to L, because I'm interested in over a length of L. I'm interested in temperature distribution of this length. Integration of 0 to L B matrix B transpose. So B transpose, have taken this here K. So here D is replaced by K because it is our convention, like we will be using a K for the thermal conductivity, which is a property of a material. And this was a B matrix. So into area into dx will give the volume. So this dV is a volume, delta volume is given by A into dx. So I'll take this A as it is out and this K as it is out, because those are the constant. I'll take it. I'll try to integrate this, and then I will simplify. Even this is a constant terms, I'll just take them out here, and the leftover is integration of 0 to L into dx, that is given as 0 to L, integration of 0 to L dx will get the value of LE. So I am writing that. So this is replaced by the LE. AK I am writing as it is, and these terms I am writing as it is. Now there is a one LE term here and there is a one L square term here. So I can cancel one of the LE and write it as A into K by LE, or if I take this outside common L square outside, it will be LE divided by L square E, 1 LE square. So I can cancel one LE and I'll be getting this term A into K by LE into 1 minus 1 minus 1 1. And already I hope you know how to multiply this term, how to get this term, because it is a row into column. So minus 1 it becomes plus 1, L into L square, and minus 1 into minus 1 is minus 1, L into L is L square. Similarly, 1 into minus 1, L into L square is L is equal to L square here, and this is 1 divided by L square. So this will be a 2 by 2 matrix. So after simplification, we will be getting what is called as a thermal conductivity matrix, which is similar to our stiffness matrix, like it was AE by L into 1 minus 1 minus 1 1. Only the difference is, in a structural we will be using Young's modulus, in a thermal we will be using a thermal conductivity as a constant. So with this we can write A is the area of a cross section of the element, K is the thermal conductivity, and L is the effective length. So this is how I can write. This is the area, length, and K is a property. Now let us consider, like this is a wall. I am heating at this condition. I know the temperature of this, and I know what would be the temperature of this, because I know the conduction is happening from one end to the another end of the portion. So for that we have derived this stiffness, this conductivity matrix. Now if air is flowing at one end of the other end of the solid body, let us consider the temperature of that as a T infinity. Let us assume that air is flowing over this surface. In the sense, the heat will be transferred from this position to this position, and from here the hot air and the temperature is taken away by this temperature. In the sense, there are two rate of heat transfers are taking place, one through a conduction, another through the convections. So let us derive what happens during the convection. So for that I have given an example here. One end of the surface is subjected to a temperature T1, other end is subjected to a temperature T2, and there is a property of a K here, which is thermal conductivity. For that we have already derived the equation. Now there is a temperature T infinity, which is a air, and this will be the a convective heat transfer. So I cannot apply the conduction law here. So I have to apply the convection law here. So the same is explained here in the top. You can read out. For that, a contribution of a convection to the stiffness matrix can be found by using this equation, wherein it is a double integration of A. H is a property convective heat transfer coefficient, and N transpose and N are nothing but the shape functions over an area dA. So just you have to substitute the N values here and derive the equation. And here N1 and N2 are same, but at node 1 convective heat transfer coefficient is 0 because it was constrained here. So there is no air here. In the sense, there is no effect of the air at this location. So that's the reason at node 1 we can take directly n1 as 0, and at a node 2 x2 x is equal to x2, x2 minus x1 by is equal to LE divided by LE. I will be getting 1, and also it is evident from the boundary condition like the node 2 surface, this other right side of the face is subjected to air. In the sense, there is an effect of the convective heat transfer factor here, so that will be taken as a 1. Now I can use n is equal to n1 n2 0 on left hand side because it is not subjected to air there, and at a node 2 it is 1 because the air is taking away the heat. Now T n transpose can be converted as 0 1, like a row is converted into column. Thus if I multiply this, if I take this one h as it is n nt into n, so that can be cross multiplied like this into this is 0, this into this is 0, this into this is 0, this into this is 1. So it will be a matrix of h into 0 0 0 1 integration of dA. Thus convective matrix at a free end is given by h into a into 0 0 0 1. So only at a node 2 there is a effect of the convective heat transfer. Now for a given structure, if I consider this as a body, this is a T1, this is a T2, and there is a air here and it has a T infinity. How much of the heat is generated here is given by this F factor, which is given as H. It is a heat transfer coefficient of air. A is the area that is exposed to air, and T infinity is the temperature of the air or a fluid medium into N1 N2. N1 is 0 because this sand is not exposed to the air. N2 is 1. So that can be written as H into A into T infinity into 0 1. Now equilibrium equation can be written as K into T is equal to F. So here K refers to thermal conductivity, T refers to temperature, and F refers to the heat that is added to the system. You know that there is a air and it has some temperature, and the effect of this temperature will be there on this one. So that will show what is the amount of a heat that is added to the system. So from the equilibrium equation I can write K is equal to Kc plus Kh. Kc is the conductivity matrix, we have derived this, and Kh is the heat that is taken away or added by the fluid medium. That this is convection and this is a conduction. Into T, I want to understand what is the temperature at node 1 and at node 2. So that is T1 and T2 is equal to how much of the heat is added by or removed by the convective heat transfer, that is T infinity. So that is written on the right hand side. So this gives the equilibrium equation for a 1D heat transfer analysis. So we will be using these equations to solve the problems in a future lecture. Thank you.